Now that we've discussed lower bounds and ways to show that certain codes cannot possibly exist, let's try to be a little more positive and see some actual examples for code that do exist and do work and are actually impressively good. So that's the content of this chapter. The first code I want to talk about is not really Hamming code, but an even simpler and precursor to that. And that's called a parity bit. So what is that? It's a very simple idea. Suppose you're given this message of bits, and you just add a single extra bit, which tells you whether the number of ones in that message was even or odd. That's all it is. A fancier way of saying that is you take the XOR of all the bits that you've sent. Now XOR is this exclusive OR. It's 1 if exactly one of the input bits is 1. And here, so you apply this to the first two, then you take the result, compute the XORs. I should probably put a parenthesis in. So you take the result of the first two XOR that with the third bit, take that result and add it to the last one, etc. It's often written with a circled plus because it's the same as really adding those numbers, but then computing modulo 2 on the result. So it's the addition modulo 2. That's another fancy way of saying XOR. But really, parity bit is about the simplest thing you can do. It's obvious that this can correct a single bit mistake, because if one of those bits flips, then of course the parity will be wrong. It will flip, it should flip from whatever it was to whatever it wasn't. And you can detect this. And that's also all it can do. If you think about it, it has code distance 2, because exactly flipping one bit makes the parity bit invalid. But then whenever you flip 2 bits, that actually brings you back to the same parity. That might take a little thought, but so the code distance is only 2. And that already tells you, if you go back to the slide from before, that you cannot correct anything. You cannot correct any, even a single bit, if that was wrong. But you can detect at least one bit. Incidentally, you can actually detect whenever there was an odd number of bits that were flipped, but that's not as useful, because if 2 bits flip, you don't see it. Still, if flipping bits are very, very rare, it's unlikely that you see those, then parity bits are fine, and they're very simple to do. So that's why they're often used in low-level protocols, in hardware protocols, because it's also easy to compute XORs in hardware. That's the simplest thing. They're simple and cheap, but in terms of a code, they're not that exciting. They cannot correct any mistakes. So let's try to move on to something more interesting. But before that, I'd like to repeat that question from before. So let's think again about how many extra bits you have to add to a message so that you can detect a single bit error. Okay, bear with me for a second to start the question. There you go. Now you should be able to see the question. How about Roman numerals this time? Whenever you're done, you send it on the chat, but this time as Roman numbers. This is what happens if you let a nerd teach. I realize I should have said whether I want capital or lowercase Roman numerals, but both is fine, I guess. Okay, seems answers are floating in. I'll give you some 15, 10, 20 more seconds. Because you thought about the question before, so I think we can cut it a little short. Okay, I'll stop in 3, 2, 1, go. All right, so this is not that helpful. Let's see the histogram. Okay, okay, it's still, okay, let's look at the actual numbers that you sent. So we have a lower bound of some very small number. Someone also just sent 0. And no 100 anymore. A couple of bigger numbers in between too. No, that's not where I wanted to go. Sorry. Yeah, so the question is a little ill-posed because it depends how long the message is. Right? The answer is really 1 extra bit is enough. So you can get k plus 1 divided k. And as I guess some of you figured out, this can be as close to 0 as you want it to be. But of course you need bigger and bigger blocks, and so that means there's more chance for this error to happen. But it's maybe surprising if you think back what you voted before and what you voted now. I suppose for most of you the answer has gone down significantly. Maybe you didn't think about parity bits up front. If you've never seen it before, maybe you haven't, you didn't think of that when I first posed the question. So detecting a single bit error is actually very cheap. But let's get back to the more interesting stuff. We want to correct codes. Now, in case you need a motivation for why this is interesting, suppose you have some server running a very important system, a very important web service, and it's, well, it has lots of main memory. Now it does happen, even though it is unlikely, but it definitely happens that things like cosmic rays, completely out of your control, flip a random bit in the large main memory of your server. Now, if you think about that this bit could be part of the machine code of some program, flipping a single bit could actually just completely destroy the application. It could completely crash the whole server. There's an interesting blog post that I linked here if you're interested in that. It's nice to read how someone traced down exactly that there was really a bit error that caused a crash on his system. And it also has some, well, some guesses about how likely that might be. The point is you can't really avoid these. They're unlikely, but for any individual bit to happen. But if you have a server with a massive main memory, it's actually a sure thing to happen once in a while. So I think the post has links to numbers by Google who tried to measure this and figure this out for their massive compute centers. So in this case, you definitely don't want your server to crash because your clients will pay you less if your server is not as reliable. So wouldn't it be great if you could just keep running and correct this error in the RAM? And this is what servers really do. Error correcting RAM exists. I think it's less prominent these days because they became more reliable, just in general, that the bits don't flip as often. But this is definitely real-world technology that is used. So how can we do this? Can we correct a bit error without knowing which bit was flipped? That might seem tough to do. I asked you to estimate how much extra memory you need to do that. Here's a simple thing. Simply take every bit and store it thrice. Whenever you see a 0, you actually store 0, 0, 0. When you see a 1, you store 1, 1, 1. Now suppose a single bit flips. If you read a bit, you actually see 3, and you take the majority of those. If there's more ones than zeros, you take 1 as the result, otherwise you take 0. If only a single bit flips, that still gives the same result. As long as not 2 of 3 bits flip, you will be able to recover from that error. So this is maybe the simplest error correcting code for a single bit error. Now, if you think about the redundancy here is 200%. That's massive. You triple the cost. Main memory is expensive, so if you tell your boss in the company you work, I can make it much more likely to have a highly reliable server, I just need 3 times as much money for doing it, he might not like that idea too much. And the amazing result that will be the end of this unit is you can do it with roughly 10%, 11% redundancy instead of this 200. And you still get the same type of guarantee. If there's a single bit error in one of the words of memory, you will be able to recover it from it and correct it. I hope that this improvement is significant to keep you interested. And also the solution is fairly neat and elegant. So how can you do this? The problem is we can only correct a flip bit if we know which bit flipped. So the question is really about locating the error. And the idea for this is use parity bits, but several of them. And the core insight is we can use parity bits just for a subset of the bits. So when we compute the parity, we just use some of the bits of the message, not all. And if we choose clever combinations of subsets, the pattern of which parity bits are violated in the block that we receive will allow us to narrow down where the bit error can have occurred. One thing to keep in mind is that the mistake could also be in the parity bit itself. So you have to be a little careful. But still, you can do this. And here's one simple suggestion that will lead to the first error correcting code. Suppose our block, so this is the block that we eventually transmit. It has 7 bits, and they're numbered 1 through 7. Now, just to make this nicer to define, I also wrote the numbers 1 up to 7 in binary on top of it. And the way I define those subsets is by taking all the bits that have a 1 at a certain position in the binary expansion of their index. For example, this C2, the check bit number 2, the blue one takes all the bits that have a 1 in the leading digit of the binary expansion. And that's the first 4. C1 is the check bit that takes the second 1 in the binary expansion. So that's the first 2 and these 2. And finally, C0 takes the least significant bit, and that's every other bit from those 7. Now, what does that mean? What we do is we take these 7 bits, and I just say a code word has to satisfy this. So B is a code word if and only if C is 0. So, and by this I mean really B7 up to B1, and by this I mean C2, C1, C0 as a bit string. They're just all 0. All right. That defines me a curly set. That defines me some set of code words. It's not yet clear how this becomes a code, but we'll get there. First of all, observe if all 7 bits are correct, then we can compute these check bits. They will all be 0, and that indicates that no error has occurred. Okay, fine. More interesting is what happens if one bit flips. If, say, bit bi flips, what will that do to the checking bits? Maybe let's do an example on that. Say we flip the bit b2, so b3. So that becomes the negation of that. Well, this bit is not used in the blue part, so if this is the only bit error, C2 will still be 0. But this bit is used in the green part, and it used to check out to 0 before, but now we compute the XOR of the negation here. So obviously C1 will be flipped too. And finally, same thing is true for C0. B3 is used here, so this will also be flipped to 1 if you compute these parity bits as given here. And if you, okay, this is, maybe I should just copy this so that we see it on the next slide again. If you look at what happens, just by how these checking bits are defined, it's obvious that if I flip bit bi, then all the checking bits turn 1 if at that position in the binary representation of I we have a 1. So for 3 is 1, 0, 0, 1 in binary. So we will have C0 and C1 flip, which is exactly what happens. And that's again just another way of saying that C, if you represent this 3-bit number again as a decimal number, the checking bits simply encode the position of the error if a single bit error has occurred, where 0 is included as no error, and anything between 1 and 7 indicates an error at that bit. And that's it. That's the Hamming code. Let's do a quick example. So suppose, okay, this is not really the code yet. Let's postpone the example till I showed you the actual algorithm. Up to now, I've told you what makes up a code word and what happens if a single bit flips, but I haven't told you what is the message, what is the block, and how to get from one to the other. So we should do that first. So this is the picture from before, but how does that turn into a code? One observation here is that if you take the bits at powers of 2, 1, 2, and 4, they occur in exactly one of these colored constraints. So we can actually turn the arrow around and define these 3 so that C is 0, which means we can take the other 4 bits. These are our message, and those 3 bits are determined by that. So that's part of the overhead. That's the parity bits that we use. All right. So if you're given a message with 4 bits, you copy those 4 bits to these positions, the ones that are not powers of 2. Then you compute the parity bits so that they make these conditions true. And another way to say, if you just figure out how that works, you set this to 0, so that means this position, I called it P2 now, but it used to be B4. This has to be set as the XOR of the first 3 bits of the message. And similarly for the others. You can just do that. And then you put those P's, you interleave the original message and the parity bits as in the picture, and that's it. So let's do an example for that. Say the message is 0, 1, 1, 0. And now I'd like you to work this out, to work on the algorithm. I'll switch back to. Okay, maybe we need some more time on this. So the message is 0110. I want you to compute the 7-bit block that the Hamming code would compute. So it's exactly execute that code just to see that you're following up on this. I put in 5 minutes for the question. Maybe we don't need the 5 minutes. Again, let me know when you're done with this. As one of the features I'm missing from Pingo, without stopping the question, see how many people have already submitted something. I don't think they can do that at the moment. I see the first reports of people who are done. This unit would have made a lovely interactive session. We could have used someone come up to the board or do that. Well, maybe some of you now think, whoo, luckily we don't have to do that. So now you can just lean back and wait. But of course you're encouraged to figure this out. All right. I'll leave the question open, but I think it's time to move on soon. Okay, fancier ways of counting. Goody. Well, I'll keep the question open till I'm done. So you see that I just computed the 3 P's as 0, 1, 1. And now what's left is the interleaving. So I take 3 bits from D, then 1 bit from the parities. So maybe, okay. could have made this in color just to make it a little nicer. So then comes the 0. No, that's not blue. 0. Then comes the last part of the message. And so then the green bit and the purple one. Oh, sorry, that's 1. So the answer should be 0, 1, 1, 0, 0, 1, 1. Let's see. 0, 1, 1, 0, 0, 1, 1. That seems to be the majority answer. Well done. Goody. I think that's that helps to understand the code. It's fairly easy to do. I guess you can imagine that you can also do this in hardware very easily. So this is a very nice code to compute. What's not clear yet is how to decode. What we've done in the lower bound section, we just said, okay, we'll decode to the closest valid code word. That sounds a little hard to do in hardware. In that formulation, but it turns out it's also very easy for this Hamming code. Decoding is you try to do the same thing as you did before. You take this block, you compute the checking bits that we introduced 2 slides back. If the checking bits are 0, you know no error has occurred, at least no single bit error has occurred. And then you can just take out the first 3 plus this bit as the message. If, on the other hand, C is not 0, C tells you which bit has flipped, so you just flip it again and then take those 4 bits. And then you get your message. So one more time, let's try to practice that. Maybe we can do it. So let's take 0, 3 ones, 0, 1, 1. Let's take this code and you try to decode it. You try to find the message that is behind this code. Now you might want to have this slide again. Well, actually, this one is good too. So here you see the C. And this is the block I'm asking about. I can start my coloring game. All right, I didn't ask for duns, but maybe you can send them. Yeah, we didn't have the Greek alphabet yet. Why not? Yeah, nice one, thanks. I'm not good at Arabic, let alone Mandarin. But we can work our way through the Unicode alphabet. Good. I think I'll stop the question here because it's probably easy for you to figure it out, even if you haven't finished. Okay, maybe I was too quick. So we have two different answers. Only 4 people made it. So sorry, maybe I was too impatient. So let's see how this goes. I can walk you through it if I was a bit too fast. So you take the 7 bits, you compute the C values by taking those respective positions. The first 4, those 2 and those 2, and the 4 every other. And that gives you 1, 0, 0. Now that means this number number 1, 0, 0 as binary is just 4, which tells you the 4th bit counting from 1 from the left is the one that's at fault, that's been flipped. So that's this one. And that's actually the parity bit 2. So we know that this has been flipped. But in terms of the message, this actually doesn't have any consequences. You would flip this to 0, and then we actually get our result from before back. So I chose a simple example. I just took the one that we've had. So of course the message here again would be the same as before, and it would be just 0, 1, 1, 0, which happens to be the same bits here. The affected bit was one of the parity bits, and we wouldn't even have to correct it. But so this is the result of the decoding. So you would see the result a couple of slides back. So this leads to 1, 0, 0, 1. And it automatically corrected the flip bit at position 4. All right, that's the 4+3 Hamming code. The properties it has is that it can correct any single bit error. It can also, to some extent, detect. It can definitely detect any single bit error because the correction, as part of the correction, we figured out whether or not a 1-bit error has occurred. About 2-bit errors, it's a little less clear. Depending, if you compute the code distance for this code, that's something I could have listed here, but I didn't. So, but it has distance 3. So it would be able to detect 2-bit error codes potentially. Now remember, these were lower bounds. The statement was, if I want to detect 2-bit errors, then the code definitely needs distance at least 3. It does not say that every code with distance 3 is necessarily able to detect these errors. And in particular, in our case, the decoding algorithm that we are using would actually mistake the 2-bit error as a 1-bit error of a different kind and correct the result erroneously to the message that would have led to this other code word, which is closer. So in that sense, this code cannot really detect 2-bit errors because it would detect that something went wrong, but it would interpret it as the arguably more likely 1-bit error. So that's something to keep in mind. So much for the 4+3 Hamming code. You can take the construction that I've shown you and generalize that. If you start with n bits, which is a power of 2 minus 1. In our case, it was 7. So we had L equals 3. Then n works out to 7. But even if you start with any other power of 2 bigger than 7, you can use L bits, namely those at indices that are a power of 2, as parity bits using exactly the same scheme. I mean, what I've shown you here, this can be generalized. The checking bits can be generalized to any number of bits here. You just have a checking bit for each position in the binary representation of those indices. That tells you exactly how the checking bits should be defined. And so you will have L checking bits out of n as a block length. So you can use all the others, all the non-power of 2 positions as data bits, as parts of the message. And if you do your math, well, one thing you can do is you can take L equals 7. That's enough to fit 64-bit, which is the usual size of words in main memory. And 11 bits of overhead of that are enough to correct to, if you use the Hamming code with L equals 7, it will have an overhead of 11%, and it's good enough to detect any 1-bit error in a 64-bit word. And you're actually wasteful. This Hamming code would support 120 bits of data, of messages. But you might also just throw away the others and use just the 64. That's the solution that I advertised before. And I hope you agree that this code is still fairly simple. It can be implemented efficiently in hardware, which makes it suitable for the application in main memory. And it's also quite space efficient, especially if you make this L a little bigger than the 3 that we had. It's a small fraction of the block that's used for parity bits. And that also brings me to the end of this Unit 8. It's a small selection of error correcting codes. There are many more out there. Many have a little more of an algebraic flavor, but it all comes back to using parity bits in a more or less clever way, or generalizing parity bits to the remainder of integer division in more or less a similar way. So I left it with this exemplary collection of parity bits and Hamming codes to give you a flavor of these. And that concludes the unit on error correcting codes.